All right. So I won't see the chat as I'm presenting, but please feel free to put in there any questions you might have, and then I think we'll get to them at the end. Um, my name is Amir Pahlavan. I'm a new professor in the Department of Mechanical Engineering and Material Science. I joined Yale last July, so I'm fairly new to New Haven area. And our lab's name is Soft Fluid Living Matter Lab. And here there are a bunch of cool pictures of what we do. I'm not going to go through them, but again, we can come back and discuss them if you are interested. So I was asked to briefly mention my career path and trajectory in science. I'm from Tehran, Iran, and that's where I did my undergrad. I'm a first generation college student, meaning that no one in my family had gone to college before me. I was the first, and it's pretty sort of difficult to get into one of the top colleges, similar to, I guess, here. To get to the top colleges, you have to participate in this national exam, um, and you have to be basically ranked on the top, like top 0.5% or top 0.1% of the whole sort of number of people that take that exam to be able to go to one of these universities. On the bright side, once you get in, you don't have to pay tuition, so it's free. So that's why it's so competitive. But your sort of destiny in a way is decided in a day. So the exam that you take to basically enter or not enter these universities is taken over a day. So it's pretty stressful, and people end up spending many years leading up to their the last year of their high school preparing for this exam. Um, so I grew up in Tehran. Tehran is a big city, and it's next to mountains. So one of the activities or one of the hobbies I had during my undergrad years was that it was pretty easy to go mountain climbing. So you would take a bus, you go near the mountains, and you spend a day there. The nice thing was that it was free, so you didn't have to pay for anything. So that's why it was my go-to activity as well. So after that, I'll mention a little bit about my interests, how they evolved during my undergrad years. But from there, I decided that I want to do some graduate school abroad, and I applied to a bunch of different universities in the U.S., Canada, some European universities, and in the end, I ended up going to University of Illinois at Urbana-Champaign, which is in Urbana-Champaign, as the name suggests, and it's basically in a flat land. So there is a huge contrast going from Tehran to Havana-Champaign because there was no mountains nearby. But I enjoyed my time there, and after there, I ended up going to MIT for my PhD. And then after that, once I finished my PhD, I moved to Princeton University for my postdoctoral training, which is a few years of extra research you do as a postdoc so it's basically research based. There are no courses, and then after that, I've come to Yale since last semester. All right, so as was mentioned, my main interest has been always patterns in nature. I wouldn't say so. I wasn't one of these kids that I can say starting when I was 4 years old, I was interested in patterns, but I got interested in patterns. I would say between my undergrad and master's years. And then sort of that, when I'm looking back, I realized that patterns in nature is sort of a unifying theme of all the research I've done and I've looked at. And I decided to include some patterns here, but then why do we look at these patterns? The idea is that we are looking at complex systems and we are trying to come up with simple descriptions of those complex systems, basically understand them and understand what governs these patterns. And so I'll mention a few uses to them, but there are lots of uses once you understood how these happen. So one example is dendritic patterns in solidification. So this is basically how salt crystals form. And you see, it's a complicated pattern, but there is some what's the word? So it's at the same time that looks relatively random. It's a uniform. So there is some characteristic length scale, some length scale between these branches that form. The same idea applies to ice crystals, ice crystal sheets that form, or snowflakes. Um, they form these really nice patterns, and if you look closely, they might look similar. And then you go all the way to basically rivers, and if you look at basically flow networks near a sea at the scale of kilometers, now we went from a millimeter scale to kilometers, and you look at that pattern, it looks very similar. So these are very different patterns. These are very different phenomena, and their physical mechanisms would be different. But then the question you ask there is that, is there any physical governing mechanism that governs all of these? Can we understand them? And then I decided to include some other pattern formation processes that are somewhat irrelevant to the top row. One example is the water striders as they move on the water. So first question you want to ask there is perhaps, how do they stay afloat on the water? And then as they move, how do they move? And as they move, this beautiful picture shows that they create these nice, interesting fluid patterns on the interface of flow, on the interface of water. Another example that is very common, it's a common daily example, you might not have thought too much about it, is dripping faucet. The nice thing there is that every drop of water that forms goes through the exact same process, no matter where your kitchen is, what the flow rate of your water is, how fast fluid is coming out. So this is a fascinating observation, and so these kind of observations basically have fascinated me over the years. So going back to my own career, so I started my undergraduate education at University of Tehran, as I mentioned, and the reason I chose engineering back then was because you would either enroll in engineering or medical school, because that was the way to make a good living. So you wanted to sort of get a job after, and I was a first generation college student, so I wanted to go through a program that would end up giving earning most money, and engineering was one of the ways of achieving that. So then through the classes that I took during undergrad, over time I became more and more interested in fluid mechanics. So what's fluid mechanics? Fluid mechanics basically deals with understanding how fluids flow, and common examples of fluids are air and water. And there are many applications for these kind of things in engineering, right? Sort of, how do we design wind turbines? What should be the height of the wind turbine? Or in power generation, in steam turbines or gas turbines. And so that was one side, turbo machinery. Basically, that's how I got interested in fluid flows. But then there was a professor in my undergrad years that was working on complex fluids. So complex fluids are fluids that are not like water, but there is some things extra in that fluid. And those extra things give rise to interesting properties. So this is a video I've taken from University of Chicago. So you can look at, they show one example. It's a non-Newtonian fluid, or it's called non-Newtonian. It's basically a starch. And you can look at, if it's poked slowly, it behaves like a fluid. It moves around very easily. But when the guy is hitting it, when he's punching it, it behaves as a solid. So I got interested in these non-Newtonian fluids, and then so mostly on the theory side. But that whole experience basically made me very interested for my graduate school to University of Illinois. And there we started thinking about how bacteria move. I was told that some previous talks were on the subject of E. coli. So E. coli is a bacterium. These are micron scale. So imagine this is the bacterium. These are micron scale. They have this flagella, this tiny fiber behind them that propels them forward. And this image is supposed to show you that the lower one is showing the fluid flow that this bacteria creates around itself. So as it's swimming through water, it's creating these patterns around it. And the top one is supposed to show the model. So we now understand how they behave at the scale of a single bacteria. But then the question becomes, what happens if you put many of these bacteria together? Would something interesting come out, given that they are perturbing their environment? And the answer is yes. So if you put many of these bacteria, so here the white rods basically are bacteria. So this is, you're looking at a droplet. Near the edge of the droplet, you see that these large scale patterns emerge. So bacteria, even though they are individually very small, they swim and then somehow self-organize themselves into these much larger structures. So that's fascinating. The question is, how do they know, is this, because there is no central intelligent system that tells them what to do. So how do these patterns emerge? And can we understand these patterns and use that understanding for something? And that basically has led to a range of, so it's active matter. It's known as a topic of active matter or study of active matter. That has led to a wealth of studies. So you can see these same self-organization in bird flocks, in fish schools, and then engineers and physicists have tried to understand, use the understanding they gain by studying these systems and apply them to robots. Basically, here the idea is that what's the simplest rules that you can give a robot, and it's still sort of simplest instructions you can give each robot, and it still ask them collectively to do something for you, right? For instance, here you're making them create these patterns for you, but you don't want them to sort of, you don't want to give them the final pattern. You want to sort of, get to that final pattern by giving them simple instructions, and the pattern emerges from the interactions between all the robots. So these are, yeah. So that's, I guess I stopped there. Then I moved to my PhD, and in my PhD I started studying pattern formation in fluid flows. So here you're looking at a video of a bubble that forms in a capillary tube. So a capillary tube, so this scale bar is 100 microns of thickness of a hair, single strand of a hair. So this is very small scale, and this is a tube. The black color here is air, and you see this air bubble is moving. The white color here is water. It's not water, it's another fluid. But what happens is that then you see that at some point, this air bubble becomes very thin, very narrow, and it pinches off. And the same thing happens if you put a needle in a large water tank and you let that bubble rise. But now if you just look at these two videos and compare them, you see that they look very different, right? So by studying these systems, we realize that the fact that this bubble pinches off in a confined environment, meaning that in a capillary tube, whereas in this case that this is a large tank, they behave very differently. So this was some experiments I did, and I also did some simulations. So what are simulations? So these are basically you write down equations, you try to use computer programming to write programs in different languages, and then you try to programming languages, and then you do this, you let the computer do the calculations for you. So here we are looking at thin liquid films. So these are, again, simulations. We start with two liquid films that are slightly, their thickness is slightly different, but these are nanometric. A nanometer is 10 to the minus 9 meters, so very, very small. So I mentioned 100 micron is the thickness of a strand of hair. 100 nanometer would be 1,000 times less than that, okay? So when you do the simulation, you start with a uniform liquid film of few nanometer thickness, and you let that evolve. And what we see is that very different patterns can emerge depending on the thickness of these films. And there are experimental studies, so these are simulations, but there are experimental studies that also look at. So then I moved on to my postdoc years, and I decided to just give you one example, and that's the coffee ring example there. So here we were interested in pattern formation due to evaporation of droplets. So if you have ever put a droplet of coffee on a surface and you let that evaporate, so you come back after 5 minutes, you might have noticed that it leaves a ring behind. So the ring so this is the ring. Basically, and this is showing the particles. This is showing with a microscope. We're looking at the particles, how they move, and you see that these particles are moving to the edge of that droplet. So that's how the ring forms. So this is a huge problem for many applications where you don't want that ring, including inkjet printing, and some other applications. So there you want a uniform deposit. How do you achieve a uniform deposit? So what we realize is that if you mix that, your liquid, let's say in this case, let's say it's some sort of alcohol, you mix it with some water or some other liquid, then that can give you a very uniform deposition pattern. So we can change the deposition pattern or patterns. We can tune them by modifying the composition of the droplet that's evaporating. All right. So then I end with the things that my lab now is working on here at Yale. So one topic, I guess, since the movies are playing, I'll start with that. One topic is about how droplets. So these are droplets. They are not intelligent systems. How droplets interact with each other. So if I didn't tell you anything about these systems, you think that these are alive. They are doing this. These two are doing some sort of dance with each other. This one is doing a boxing match. It's sort of going back and forth. So these systems look alive, but they are, of course, droplets. They are passive. So how do they do these? And what we've understood is that they can interact. These droplets can interact through their vapor field. So as they evaporate, there's a vapor around them, and through the liquids underneath. So we are studying these systems. And another system we are studying is basically transport of colloidal particles, and colloids are micron scale, very small particles that move around because they are so small. When water molecules hit them, they bounce around. And we are studying how these particles or bacteria are transported in complex environments. So I think with that, I stop. That was my last slide, and then I'd be happy to talk more about any of these.
So first and foremost, thank you so much for your presentation. It was really, really fun. We had a really exciting breakout room. A lot of people were really interested. We got to do the experiment in mine. And so the first question that everyone's wondering, we had a lot of hypotheses in my breakout room, but why does the pepper move to the sides of the plate or cup or whatever when you have the soap on your finger?
Yeah, so the idea is related to soap is basically, okay, so the first thing we have to explain is surface tension. So surface tension is something similar to the tension in a membrane, or think of an air balloon. So when you're stretching it, it's hard to stretch it, right? So there is something that is keeping it together. So there's a tension there. So the same thing is true for the surface of a water bath. So the water molecules want to be in contact with each other, so they don't want to let anything in. And that's exactly the mechanism that the water strider uses to sort of stay on top of water. So when you put soap in the center of the bowl, what happens is that the surface tension there goes down. So when the surface tension there goes down, and surface tension is higher away from that point near the edge, then that creates a flow, because now everything wants to go from the low surface tension area to the high surface tension area. So there's there's a pull from the edge, from the center to the edge, and that creates this flow. And then the soap molecules basically start the spreading, and with that spreading, they are pushing the pepper all to the edge of the container. So that's how this thing happens. And actually, so you can repeat this experiment later and put different amounts of pepper and see what happens. If you put too much pepper, that could also be cool. So if you put too much pepper, you'll see that if you put a little bit of pepper, it should be a ring. If you put too much pepper, then you can look at what happens. So I won't give over the answer.
It's a science experiment everyone can take home. Okay, so we also collected a couple other questions during the duration of your talk. And if anyone has any other questions, feel free to put them in the chat and I'll try to get to them. So we got a lot of questions when you were showing the little simulation of the passive droplets. So
that was an experiment, actually.
Oh, that was an experiment. Okay, wow. I thought it looked like a simulation. Wow. So even more then, one of the main questions we got was, how is that even possible if they aren't alive? What is the attractive force between them? How are they moving like that?
So it's somewhat related to the same concept of this gradient and surface tension that we just talked about. Because you could say the same thing that, how is it possible that the peppers start the ground pepper starts moving? There is no it's not alive, right? So it's moving because of this gradient and surface tension. And the same thing happens there in the droplet case. What happens is that they are evaporating, and these droplets, as they evaporate, there is a vapor field around them. You don't see them. And these two droplets, these were oil droplets, some sort of oil that evaporates, and they were sitting on a water bath. So as they evaporate, they influence the surface tension of water bath around them. That creates these gradients in surface tension in the water bath. It creates these flows within the water bath that you don't again see. So these are all invisible. The only thing you see is the droplet itself. And then, so because of all these flow fields that you don't see unless you go to really extra length, then you will see that these flow fields that are generated move around droplets and lead to a wealth of dynamics that we are still exploring. So you can ask, what happens if you put 3 droplets and many droplets, and the possibilities are infinite.
Thanks so much for that answer. And kind of along that same vein, you were talking about these like invisible forces. One question we also got was, is the invisible force related at all to electromagnetic attraction? Does it involve any ions or anything like that?
No, so there is no electromagnetic force. So yeah, all is surface tension, and so surface tension is amazing phenomenon that even in college they don't teach you much. But if you guys were interested, I encourage you. I found many interesting YouTube videos about surface tension and the consequences. Go and search on YouTube. So it's all about surface tension and the cohesion between water molecules. And when you create gradients in surface tension, you can create it in different ways. One way was adding that soap. The other way is like if you have a vapor around this droplet, there is a gradient in vapor concentration that leads to the gradient in surface tension, creates a flow. You can have another case if you're heating part of your container and cooling the other part, or just heating one side. Heating would lower the surface tension, and that also creates a flow field. So there are many different ways you can create these gradients. And once these gradients are generated, they create flow fields. Basically, they make the water molecules move. And once they start moving, they create all these interesting phenomena.
Yeah, wow. I definitely, I feel like last time I learned about surface tension was when I was also in high school, and it's crazy to think that it really does really get much more complex if you keep studying it. So another interesting question we have from the chat is, how is something classified as a fluid? And is that related at all to like when you're thinking about studying fluids?
Right. So I think isn't the sort of textbook definition that fluids take the shape of their containers, but they don't uh, um, expand, whereas they don't occupy the whole volume, whereas gases do. So and then solids, so they don't move. The atoms are not moving around. So fluids typically there are 2 classes of fluids. One class is called Newtonian fluids because Newton was sort of the first person, I guess, that came up with equations or laws that describe the motion of these kind of fluids. So water is a Newtonian fluid, but many other fluids are not Newtonian. Examples of that, and honey actually, by the way, is Newtonian. So by the way, next time you're maybe if you're having honey with your breakfast, as you're pouring honey, look at what happens as it hits the surface. If you have a spoon, let's look at the contact. So it forms these coils. These are these interesting coils. So why does it form coils? So you can ask yourself that. Uh, So non-Newtonian fluids, there are many liquids that are non-Newtonian, which means that they are not described with laws that Newton came up with. And one example was that cornstarch solution that I showed. If you are mixing it very slowly, it's like a fluid. It moves around and you can shear it, you can move it. Whereas if you start punching it, it behaves like a solid, because then a time scale comes in. It's called the relaxation time scale of the fluid. For water, the relaxation time scale is very small, so you don't see anything. Whereas for more complex liquids, and they are called microstructured liquids because there is something in them. There might be a polymer in it, there might be some particles in it. There is another relaxation time scale that could be on the order of microseconds, milliseconds, or seconds, and that leads to a wealth of different phenomena.
All right, thank you. Thank you so much for explaining that. We also have another question in the chat about, is any of this related to algebra? So what type of math is involved in these sorts of experiments that you're doing?
So you can only do the experiment without any math, but to understand that you need math. So that's typically, I guess, that's the broad question about physics. You know, any physical experiment you do, typically to understand them, you need to use, I guess, okay, let's take a step back. So I'll try to explain it maybe more broadly. So there is a lot of physics, and it's sort of the branch of soft condensed matter physics, but and fluid dynamics is also part of it. But a whole part of physics, the equations are known. So the equations that describe phenomena are known, but the equations are for very simplified settings, meaning that we know exactly the equations that describe the fluid motion in the middle of the ocean. We know that. But then to solve that equation is one thing, and we have now these supercomputers to solve these equations because it's very complicated actually to solve these equations. And the second thing is that in many cases, if you have interfaces, if you're thinking about particles in your fluid, if you're thinking about interface between a fluid and an air, in many other cases, these equations don't work. So these become basically what is called typically as interdisciplinary topics, where you need to not only think about the equations that are known maybe 200 years, but you have to think about like the chemistry of the materials and what is known as sort of typically physical chemical properties. Meaning that, so these then, you need to learn a little bit about chemistry, you need to learn a little bit about physics, and you need to know math, and you try to combine them and come up with the models that describe these systems. So yeah, a lot of what we do is a combination of physical experiments and modeling, and then we come up with the models, and then we use computers to solve these models, and then we compare them side by side and see if what we observe on the computer looks like what we observe in the experiments.
Great. So yeah, so this is definitely sounds like a field where if you like algebra or if you like other kinds of math, you can definitely apply it to this field. And so I think we're getting to the end of the questions now. When you were explaining the difference between a solid and a liquid, it kind of reminded me of this funny comic I've read before about perhaps like the fact that cats are kind of act like liquids because they, can fall out of your hands. And you ever seen like cats in like little containers? They always can squeeze into them. And so we got a question at the beginning of the talk. Are you more of a cat person or a dog person?
I would say I'm more of a dog person, but there was a IG Nobel Prize exactly on the thing you mentioned. So how cats behave like liquids.
So maybe you're more of a dog person because you don't want to take your work at home. You don't need to have the liquids running around your house.
It's a good way of looking at it. Yeah, yeah.
Okay. But again, thank you so very much for speaking with us today. This has been really,
Thank you
really
for
great.
having
I
me.
learned so much, and I think everyone else would agree. So feel free to thank Amir again in the chat, and I will pass it on to another volunteer to end this session.